Hello, welcome back to the lecture series on network layer protocols of the internet model. In this video, we are going to learn about what is there inside a router, part 2. So the main agenda would be to understand the various forwarding process that the router uses to forward the data to the destination from the source. After that, we are going to learn about the routing tables. Let us now understand the forwarding process. In a previous video, we have learned about the various forwarding techniques. Now, what are the different types of forwarding process that a router can have? Simplified forwarding. Then we can have longest mask matching. After that, address aggregation. Then hierarchical routing and geographical routing. These are the various types of forwarding processes. Let us understand simplified forwarding module. So this is the nature of the simplified forwarding module. We have the packet coming from one side. This packet basically goes to extract the destination address, because we must understand here this we are using the classless addressing technique, because classful address is a part of classless addressing. Here we assume that the host and the routers use classless addressing. For classless addressing, the destination address must be extracted by using the masking technique. So this has to go to a search table. Now from the search table, there must be at least 4 columns. These 4 columns are the mask. Mask is given as /n. We have learned about masking in a previous video when we learned about the network layer. Then comes the network address column. After that, next hop address column, and last column will be the interface column. Once we get the next hop address and the interface number, we have to send it to the ARP or address resolution protocol. Let us understand the simplified forwarding module with the help of an example here. You have to make a routing table for the router R1 for this given figure. This figure shows that there is a router R1 over here. So this is a router, and this router has basically 4 interfaces: M0, M1, M2, and M3. Through these interfaces, the router is connected to 4 different networks. Like with M0, it gets connected to this network having this address. With M1, it is connected to this network. With M3, it is connected to this network. And with M2, it is connected to this network. And this network basically gets connected to the rest of the internet through this interface. You have to make a routing table for R1. Let's see how to do it. So as before, we know that there must be 4 columns: the mask, the network address, the next hop address, and the interface. So initially, first, the masking is 26/26, and the extracted network address is 180.70.65.192. So the next hop address will not be there because the router is directly connected to this network, and it is through interface M2. Next, the mask is /25, and the network address is 180.70.65.128, and the next hop address field will be blank, and the interface is M0. After that, we have /24 with the network address 201.4.22.0. Next hop address field is blank, and interface is M3. Next is /22 with a network address of 201.4.16.0, and interface is M1. And if the router wants to get connected to any other network to the rest of the internet, the next hop address should be 180.70.65.200, and the interface should be M2 as per the previous figure. So for your reference, I have redrawn the figure here, so you can just make a comparison of the figure with the routing table. Next, we go to address aggregation. Address aggregation is a process by which the longest routing table is reduced. Let us see it with the help of this example. There are 4 organizations, organization 1, 2, 3, 4, having certain addresses, and these are connected to router R1 through interfaces M0, M1, M2 and M3. And this router R1 has another interface M4 through which it gets connected to the router R2, which is somewhere there in the internet at a far off place from router R1. This router R2 again has 2 interfaces. M0, with M0 it can get connected to router R1, and with M1 it can get connected to other networks. Let's see how to form the routing table of R1 and R2. It is clear that the routing table of R1 will be longer because there are different networks that are connected to router R1, and that of routing table for R2 will be a smaller one. So routing table for R1 will be, there are 4 organizations. So /26 network address given as 140.24.7.0 with the interface M0. This is for organization 1. For organization 2, we can have it through interface M1 having the proper masking network address and next hop. This is for organization 3 and this is for organization 4. And if it wants to get connected to the rest of the internet, it can have this type of masking network address and network next hop address, and with the interface will be M4. Now the routing table for R2 is very small. There are only 2 fields. We can have 2 rows for /24. So this is the interface M0 through which it can get connected to router R1, and from there to various organizations 1, 2, 3, 4. And this is the default one with which it can get connected to the rest of the internet. Now there is another forwarding process which is called longest mask matching. Let us consider that as before, these organizations 1, 2, 3 are closely associated with router R1, but organization 4 is far away. Now how to actually get connected to organization R4 and with the help of this routing table R2? So let us understand them one by one. So as per the figure, the routing table for R1 will be like this as given here. So there are basically 4 different interfaces. Through interface M0, it can get connected to organization 1. With M1, it gets connected to organization 2. With M2, it gets connected to organization 3. And with M3, it can get connected to other parts. Now here we can see here this with the help of M3, a router gets connected to router R1 gets connected to router R2. Now router R2 has an interface M0 through which it can get connected to router R1. This router R2 again has 3 interfaces, M0, M1 and M2. Let us look at the routing table of R2. So with the help of M1, it can get connected to other parts of the network. With M0, it gets actually connected to R1, and there is a default M2 by which it can get connected to the rest of the internet. Now here we can see here this is router R3. This router R3 actually again has 3 interfaces, M1, M2 and M0. With the help of M2, it's get connected to router R2. With the help of M1 to other networks. With the help of interface M0, it can get connected to this network and finally to organization 4. So this is the total figure. We can see here that these 3 organizations 1, 2, 3 are aggregated. So this is known as aggregation. Whereas organization R4 is far away. Now what if we have this thing, let's say we have a destination 140.24.7.200. If this is the destination address, how to properly go to organization R4? So for that purpose, let us switch back to the router R2. Here we have, see here, we said that the destination is 140.24.7.200. Now, the longest mask matching means it is properly segregated or reordered, as the longest mask should be at the beginning. So /26, then /24, and then the rest. So once the destination address comes, the router has to give the masking, proper masking 26. So if it gives this masking, it gets the network address, this one, 140.24.7.192, and it properly identifies the network address and properly goes to the organization 4. But if it would not have been reordered in the form of longest mask matching, then it would have given the /24 masking and it would have arrived at this network address. But this network address is not for organization 4, but rather it is for organization 1 through R1, and it would lead to wrong addressing. So this is the utility of longest mask matching. Next, let us look at hierarchical routing. We know that internet has a hierarchical nature. It is divided into international as well as national ISPs. These national ISPs are again further divided into regional ISPs, and these regional ISPs are divided into local ISPs. So in the same manner as the internet has a hierarchical nature, the routing also can be hierarchical, which will greatly reduce the routing table. So this is the example of hierarchical routing. You see here there is a ISP which has a total of 16384 number of addresses, and it is a single but large block of addresses. Now this block is further subdivided into 4 different blocks having a total of 4096 each, giving a certain addressing range. Now each of these again are further subdivided into 4 different address pools having 512 each. So in this fashion it goes till the last one, when we have the host from 001 to host 128. So like this. So here the rest of the internet has no idea that there has been a hierarchical process in the local ISPs. So to the rest of the internet, the routing process becomes very easy, because if there is any computer or host, suppose this is the host, so to the rest of the internet, it does not need to know about the hierarchical process, but it simply forwards the data to this ISP. Now this is the function of this ISP to properly forward the data to the proper destination. So this greatly simplifies the hierarchical process and the forwarding process. Next we have geographical routing. This geographical routing is a form of hierarchical routing, and we can see that it is an extension of hierarchical routing to further reduce the size of the routing table. Here you see the entire internet service providers of the world are divided into several blocks. Now each block is allocated, let's say, to a particular continent. Let's say we have North America, Europe, Asia, Africa, Australia, and so on. So these are divided, and routers of these ISPs of, let's say, North America, there will be only one entry point. So routers of ISPs outside the North America will have only one entry point. Similarly, routers of ISPs outside Europe will also have single entry point. This way, it can further reduce the size of the routing table by using geographical routing. Let us now concentrate on routing table. Routing table basically helps in forwarding process. So there are two types of routing tables. One is called the static routing table and the other one is called the dynamic routing table. In static routing table, manually data is fed to the routing table. If there is any updates or deletion of the data, then it has to be done manually and not automatically. Then we have the dynamic routing table where the updating, insertion, deletion of data from the routing table all is done automatically. And this basically takes place in on-demand basis. What is the format of the routing table? The format of the routing table will have these fields like the mask. Already we know this is the mask to get the network address. Then this is the next stop address to the destination. After that, the interface through which the router has to forward the data. Then we have the flag fields. There are basically 5 different flags. The 5 flags are U flag, G flag, H flag, D flag, and M flag. If U flag is set, it means that the router is up and it is running. If G flag is set, it means that it is a gateway flag, which means that the data must be forwarded to the other network. And it is an inter-domain routing. If H flag is set, it means that it is the host-specific type of forwarding. If D flag is set, it means that the message has been added to the router by redirection through the ICMP. If M flag is set, it means that by redirection through ICMP, there has been a change in the data. Now there is a reference count which indicates that how many users are there. And there is a use field which indicates how many packets have been transferred. Next we go to utilities. Utilities mainly are used to find the routing information and contents of a routing table. There are 2 types of utilities that we will be learning here. One is the netstat. Netstat basically will help us to find the routing information of a host or a router. For example, this is the Unix or the Linux command. We write here netstat -rn. So it basically gives the kernel IP routing table. This is the destination and it gives the gateway, then the masking, then the flags field and the interface field. Interface field here, and we can understand here, this is the Ethernet port 0. This is also the Ethernet port 0. If it is I0, it means it is the loopback address. The next utility that we will be learning is the ifconfig. It is basically used to get the IP address and the physical address of the server. ifconfig ETH0 is the Linux or the Unix command. If you give this, you get this result. It gives basically the hardware address. This is the NIC, and it gives the Ethernet address, the broadcast address, and the masking. So you can get a clear idea about the IP address and physical address of the server. So this is an example. Suppose we have the ETH0. This is the hardware address, and we have the default router here, which is connected to the rest of the internet, and it basically gives the masking as well as the network address and the interface address. To summarize, in this video, we have learned about the various forwarding processes. We have learned how the simplified forwarding process is operated. Then we have touched upon hierarchical routing, geographical routing, longest mask matching, as well as address aggregation. Then we looked into the routing table. We understood what a static routing table is and what a dynamic routing table is. Then we looked into the format of the routing table and the various utilities like, for example, ifconfig and netstat. Thank you.